It is the middle of July. The sun is beating down. The asphalt is melting beneath your feet, and the air feels like an oven. You walk inside your house, hear the steady hum of a machine, and instantly, a blast of freezing air hits your face. We often think of this machine as something that creates cold air. In the realm of physics, however, cold is not a substance or a type of energy. It is simply the word we use to describe the absence of heat. Your air conditioner operates by violently ripping thermal energy out of your living room and throwing it outside. We achieve a comfortable home through this systematic relocation of energy, turning the air conditioner into a mechanical fief. To steal heat, you need a specialized accomplice. In an AC system, that is a highly engineered chemical called a refrigerant. When water evaporates on your skin, it absorbs your body heat to fuel its transformation into a gas. An air conditioner uses a chemical with a sub-freezing boiling point that travels endlessly through a closed loop of copper pipes connecting the inside of your house to the outside. The process begins at the evaporator coil inside your home. The refrigerant enters these pipes as a freezing, low-pressure liquid, while a fan blows your hot, humid room air directly over them. Because heat always seeks out cold, the thermal energy in your room leaves the air and transfers into the freezing pipes. This rush of room heat causes the refrigerant to instantly boil, where it flashes from a liquid into a vapor, trapping the stolen energy inside the gas. The air blowing out the other side of the unit feels freezing because the boiling liquid has successfully robbed it of its heat. Now the system faces a problem. The pipes are full of gas holding the stolen heat, but that heat must be dumped into an outdoor environment that is already 40 degrees Celsius. Since heat naturally flows from hot to cold, the gas inside the pipes must become hotter than the summer air to escape. This happens at the heart of the system, the compressor. This is the loud, vibrating motor sitting in the unit outside your house. The compressor acts like a powerful fist, crushing the gas molecules closer and closer together. As the pressure spikes, the temperature of the gas skyrockets to a blazing 70 degrees Celsius, much hotter than the air outside. This superheated gas flows into the condenser coil, where a fan blows the 40-degree summer air over these 70-degree pipes. By forcing the gas to be hotter than the sun-baked air, the laws of physics allow the stolen heat to naturally dump into the summer breeze. Having released its heat into the atmosphere, the refrigerant cools down and condenses from a gas back into a liquid. However, this liquid is still under the intense pressure of the compressor. It must relax before it can return inside to steal more heat. It travels through the expansion valve, a tiny pinhole where the pressurized fluid goes from being tightly squeezed to suddenly bursting into an empty space. As the pressure plummets, the temperature instantly drops back to freezing. Suck the heat in, boil, squeeze, dump the heat out, expand, repeat. In 1902, Willis Carrier developed the mechanical process that allowed us to finally dictate the temperature of our surroundings. By controlling the internal climate, we were able to build massive glass facade skyscrapers that would otherwise become uninhabitable solar ovens. It allowed for the growth of massive cities in desert regions where the summer heat previously made permanent settlement difficult. This same heat death technology now prevents the hardware in global data centers from melting down under the stress of powering the internet. The modern world relies on this precise ability to move heat, allowing us to inhabit the desert and sustain the digital lives we lead today.